All right, let's get right into it. Think about world maps for a second. We see them everywhere, right? In classrooms, on our phones. They feel so solid, like a perfect, true picture of our planet. But what if I told you that every single world map you've ever seen is, well, a lie?
I mean, take a look at this one. You definitely know this map. It's almost certainly the one you had on your classroom wall. Its official name is the Mercator projection, and it's been around since the 1500s. And you can see why it's so popular, right? Everything's a nice, neat grid of straight lines. It just feels right.
But that feeling of rightness, is it actually right? Is this neat, tidy grid really showing us the world as it is? Or is it telling us a story that's just convenient, but maybe a little bit warped?
Okay, so here's where it gets really obvious. Take a look at Greenland versus Africa on this map. They look kind of the same size, right? Well, in the real world, Africa is 14, that's 1/4, times bigger than Greenland. That's not a tiny little mistake, it's a huge, massive distortion. And it's really the key to unlocking this whole idea that every map has a lie built right into it.
And that gets us to the heart of the matter, what you could call the map's big lie. Now, it's not like cartographers are trying to trick us. It's just an unavoidable problem. It's baked right into the process of making a map.
The problem is just basic geometry, really. The Earth is a sphere. And a map is flat. And you just can't flatten a sphere without messing something up. You have to stretch it or tear it or squish it. The U.S. Geological Survey says it perfectly. It's impossible to make a flat map of a curved surface without distortion of one form or another.
Here's a great way to think about it. Imagine peeling an orange and trying to lay the peel out perfectly flat on a table. You can't, right? You'd have to tear it or stretch it to make it work. That's stretching and tearing, that's distortion. And it's the exact same challenge mapmakers have been dealing with for hundreds of years.
So, how do they deal with it? Well, the method they use is called a map projection. It's basically a mathematical formula for how you're going to translate the 3D globe onto a 2D piece of paper. The official definition calls it a systematic representation of the surface of a round body on a plane. Think of it as a set of rules for that orange peel.
And to come up with these rules, cartographers get creative. They imagine wrapping the globe in a shape that can be unrolled perfectly flat. These are called developable surfaces. The most common ones are a cylinder, like wrapping a can around the globe, a cone, like putting a party hat on it, or just a simple flat plane touching one point.
And this brings us to a really crucial idea. Since you can't get rid of distortion, the whole art of making a map becomes about choosing your distortion. It's not about being perfect, it's about deciding what you're willing to get wrong.
See, when you make that translation from 3D to 2D, you're forced to mess with at least one of 4 key things. Area, how big things are relative to each other. Shape, what the land masses actually look like. Distance, how far apart things are. And direction, the compass bearing from one place to another. You simply cannot preserve all 4 of them on a flat map. It's impossible.
Which leads to what's basically the golden rule of mapmaking. The USGS puts it bluntly. No map can be both equal area and conformal. Okay, what does that mean? Conformal just means it preserves the correct shapes, and equal area means it preserves, you guessed it, the correct area. So you have to pick shape or size. You can't have both.
So that's the big trade-off right there. What's more important for what you're doing? Do you need a conformal map, one that gets all the local angles and shapes just right? That's what you want for navigation. Or do you need an equal area map, one that shows you the true relative size of countries? That's absolutely vital if you're trying to compare things like data across different regions.
Okay, so let's make this really practical. Because the right map is really just about having the right tool for the job. Let's look at a few different jobs and see which map they'd pick.
First up, imagine you're a sailor back in the 1500s. You're trying to get a ship full of cargo across the Atlantic. What's the #1 thing you need from your map?
You need the Mercator projection. Yeah, the very same one that makes Greenland look huge. Its biggest flaw, that crazy distortion of area, is actually a side effect of its single greatest strength. Because it's a conformal map, it preserves angles. What that means for a sailor is that a line of constant compass direction, what they call a rum line, is a dead straight line on the map. That is a game changer. You just draw a straight line, point your ship in that direction, and you'll get there.
All right, new job. Now you're an airline pilot. You're flying from New York to Tokyo. You don't care about a constant compass bearing. Your main concern is finding the absolute shortest, most fuel-efficient route possible.
For that job, you need a totally different tool, the geomonic projection. Now, this map's special trick is that any straight line you draw on it is what's called a great circle. And a great circle is the shortest possible distance between 2 points on a globe. So that weird, long, curving path you see on most maps, on this one, it's a straight line. It looks totally strange to us, but for a pilot trying to save time and fuel, it's perfect.
Okay, one last job. Let's say you're a geographer or a data analyst, and you're trying to compare something like population density or resource distribution across different countries. What's your number one priority?
For that, you absolutely need an equal area projection, something like the Albers. And just look at how different it is. Yeah, the shapes up near the poles get all stretched and weird, but that's the trade-off. What you gain is that the size of every country is correct in relation to all the others. And that is crucial. If you tried to compare data using a Mercator map, your conclusions would be completely, wildly wrong.
So where does all this leave us? Well, it shows us that the world of map making is really a world of compromise. It's all about making choices and accepting trade-offs.
And the big takeaway here is that there is no such thing as the one best map. It's like asking what the best tool is in a toolbox. Is it a hammer, a screwdriver? It depends on the job. The right map is simply the one that's been designed for a specific purpose, to tell a specific kind of story. Every single projection is just a different lens for looking at our world.
So, from now on, whenever you see a world map, I hope you don't just see a picture of the Earth. I hope you'll ask yourself, wait a minute, what was this map made for? What is it showing me perfectly, and what is it distorting to do that? Because if every map is telling a story, isn't it worth knowing what story you're actually being told?